Now that we have seen a valid solution to the critical section problem, let's look into how hardware can help us in this context. As mentioned in previous lectures, collaboration between the operating system and the hardware is essential, and it can be observed in many modules and aspects of modern operating systems. The first option we look at is a function that allows users to disable or enable interrupts on one specific core, as shown in the slide. Such a function could, in principle, help, but you probably agree with me that disabling interrupts can lead to limited ability of interleaving programs. In a sense, the user might be given too much power and limit the operating system control. More importantly, the problem with this solution is that by disabling the interrupts on one core, threads running on different cores are still able to lead to behavior that does not satisfy the critical section problem. Something better is provided by read, modify, write operations. In this case, we are not talking of individual atomic reads or writes, but of an atomic operation that performs both a read and a write. Examples of these operations are test and set, fetch and add, compare and swap, and so on. We will look at some of these next. Let's try with the test and set instruction. As shown in the slide, the function gets a Boolean variable, sets it to true, and returns the previous value. As I said, this instruction is executed atomically, so it either runs in its entirety or it does not. Under the hood, the hardware is either disabling interrupts if the system is uniprocessor or locking the system bus if the system is a multiprocessor one. Now, if you think about it, you will agree with me that if the target variable is set to false and n concurrent threads invoke the test and set, then only one will get false in return. If you agree with this, then probably you can see how we can use the test and set in the entry section as shown in the example. A thread can enter its critical section only if the test and set returns false. If there are concurrent invocations, the test and set will only return false to one thread, and no other thread will be able to enter its critical section until another thread exits its own and sets lock to false. Please take a moment and try to reason formally about whether this solution meets the mutual exclusion, progress, and fairness properties. An alternative instruction we could use is the compare and swap. In this case, the instructions that are run atomically will set a given value to a given variable only if the current value of such variable is the expected one. If you look at this alternative formulation of the critical section, you will see it's equivalent to the one using the test and set. Something worth noticing about these solutions is that they are busy waiting spinning. Each thread will keep consuming CPU cycles until it manages to enter its critical section, which is a waste of resources. If you have tried to argue yourself about whether these are valid solutions to the critical section problem, you probably have reached the conclusion that from the fairness perspective, they are also not optimal. More concretely, they can lead to starvation, with the same thread being the one that keeps entering its critical section and other threads not managing to do so. The third point to think about is the underlying operating system scheduling mechanisms. Even if in this lecture we have not really made any assumption on the scheduling mechanism the underlying operating system is using, you should not think we do not need to make assumptions when looking at a specific solution. For instance, if we assume the operating system is running a non-preemptive priority-based scheduler and the thread that is spinning in its entry section is the one with the highest priority, then the solution can lead to a deadlock and no thread is actually able to make any progress. If we now go back to the observation about starvation, let's look at an alternative formulation that can help us achieve better fairness. Let's assume the entry and exit sections are as shown in this slide. Besides a shared lock variable initially set to false, we have a shared array of Boolean values called waiting. The array has one Boolean per thread, initially set to false. In its entry section, before entering the while loop, each thread shares its will of entering the critical section by setting its entry in the waiting array to true. The thread will stay in the loop until it manages to run test and set, as before, and while its waiting entry remains true. After exiting the while loop and before entering its critical section, the thread sets its entry in waiting to false. Now let's look at what happens after the thread exits its critical section. The thread circles over the waiting array, starting from the next thread in the array, as if the buffer is circular, and then stops as soon as it finds one entry for which waiting is true, or if it completes the circle. If no other thread is waiting in its loop inside its entry section, then this thread sets lock to false. So some other thread that wants to enter its critical section later on can do so. Notice that the thread that enters its critical section next could be the thread that just set lock to false, but this cannot happen for an unbounded number of times, since if another thread also wants to enter the critical section, then its entry in waiting will be true, and the thread that manages to enter its critical section will then hand over the lock in its exit section, as shown in line 14. As before, try to formally reason about whether this solution is valid or not by yourselves.